And one of the things that we did was use reactive species to improve productivity. So if each cell produces more, then there's a possibility of it being competitive. So at that point in time, when you stress the cells, they produce more oil, but the growth will go down. That was the conventional wisdom anyway. That was known at that time. Stress in various means. Okay. They didn't really associate it with reactive species, although the background it was known and so on and so forth. So we were the ones who directly went into reactive species induction and things like that. So the if you stress the cells, the oil yield will be more, but the growth will be less. So then Ranjani figured out a strategy by which you could grow cells first through an appropriate lighting strategy, and then stress the cells appropriately and simultaneously improve both the cell yield as well as the oil yield. That was her thing, and she was the one who got us into the rhythms of reactive species. She was the first one. She was the first one in the lab to look at rhythms. I had not looked at rhythms at that point in time. She came and showed me this data or similar data and said, there are rhythms here, we'll look into it. I said, good, look into it. And then she figured out how to look into it. She figured out the Lomsky-Argel periodogram and so on and so forth. And then said, these are the ways by which you can analyze it. Good. Then we figured out a story together and wrote up the paper, as simple as that. And then figured out that it indeed was important. It's indeed an important determinant. That came slowly, that the rhythm period is an important determinant in all these things. Okay. The fact that the reactive species level doesn't remain the same, the pseudo steady state level doesn't remain the same. It goes through all increases and decreases with time under regular conditions, under physiological conditions. And if you can characterize that rhythm through an amplitude and a period, right? It's a wave, so amplitude and a period. So if you change that period, then a lot of desirable things can happen. That's what she figured out. So in other words, the level is not important, but the way the level changes is important. So that brings in a comprehensive view to the reactive species level and therefore the oxidative stress levels in the cell. That was her contribution. This she did it with microalgae, and then we moved to cancer. That I'll tell you later. So this is the way you characterize the variation. This is on a time scale. If you look at this, this is specific intercellular hydroxyl radical levels versus time. There is variation, but if you want to characterize it, it's not so easy to characterize it on a time scale. Therefore, you need to convert it into a frequency scale. This is a well-known technique in control analysis and so on and so forth, right? All your Laplace transforms are based on that technique. And if you convert it into a frequency scale, then these things show up nicely. The frequencies at which you have the characteristic variation shows up, and then you can choose the appropriate frequency if you put off a cutoff level for the confidence with which you can, these are confidence levels, confidence with which you can believe your data. So here we could very clearly see for the hydroxyl radicals, this is the spectral power as it is called, intensity essentially. Oscillation of hydroxyl radicals happens at 0.167, somewhere here, R inverse frequency, that translates to about 6 hours of time period. So circadian is about 24 hours, ultradian is less than 24 hours. So this is an ultradian rhythm of hydroxyl radicals in the light phase, and there was none in the dark phase for this regular lighting period. 16 hours of photosynthetically active radiation, which is equivalent of sunlight, and 8 hours in the dark. Whereas here, if you change, if you bring in some UV, then you can see from here itself the pattern changes. The pattern of variation of hydroxyl radical rhythm changes. This was 5 hours of PAR followed by 6 hours of UVA followed by 5 hours of PAR. This accounts for 11 plus 5, 16 hours of light and of 8 hours of darkness. Right? So this is what she did. And then this is what she found for the regular this lighting. And for this lighting, this is what happened. When she changed the lighting strategy, then in the light phase, there was a change. The oscillation happened at 0.34 hour inverse, which is 3 hours approximately. Earlier it was 6 hours, now it is 3 hours. And there was an addition of or an inclusion of an oscillation in the dark phase also. Earlier there was no oscillation in the dark phase. So here it happened at 0.26 R inverse or 3.8 hours. So this led to, these are rose plots. This is specific lipid accumulation levels, lipid per cell, lipid is a product, right, oil. And in the regular thing, this is from 12 a.m. to 10:30 p.m. a rose plot. The distance of this vector gives you the amount that you're looking for, concentration that you're looking for. So as you can see, if in the standard lighting 16:8, the accumulation happens from here to here, right? Over how many hours? This is about 6 hours, is it? 12 to 6, a little less, yeah, about 6 hours and so on and so forth. And the amount accumulated is this much. Whereas under changed lighting strategy, the accumulation happened almost over 12 hours and the amount was a lot more because of the reactive species that were induced. Okay, we have proof of all that. Reactive species levels were measured, hydroxyl radical levels were measured, and so on and so forth. And she also has a mechanism by which this happens by the reactive species. And all this was published in Biotech Progress. Biotech Progress is the second most prestigious journal in our field overall. Biotechnology Bioengineering is the topmost for our kind of work, and Biotechnology Progress is for the second in my view. Yeah, these were the two papers in AICHE journal. I think one of them was required reading for you. The other one, second one is required reading for you, and the first one was an optional reading for you. And then this was optional. This is a nice strategy, so we'll end with this. I hope we'll end with this. Yeah. So this, you see a spectrum here, right? Typically, this is in a train station. So you have, although it is PAR, photosynthetically active radiation, you have a set of frequencies that constitute the PAR, and you have in the infrared region and the near infrared region something that is coming in. All this comes in, all this is available from sunlight. In the case of photosynthetically active radiation alone, you have a certain level of growth. In the case of photosynthetically active radiation and conversion of the infrared radiation into photosynthetically active radiation, you're going the opposite direction, right? That's not easy. It's increase in energy. You're going to, you're going to higher frequencies, so increase lower wavelengths, so increase in energy, and you needed to have something to do that. If you do that, then you could get better growth and so on and so forth with less heat. So lesser heat damage and better sunlight utilization was the idea at this point in time. It was already known at that time there are something called uptransfer phosphors or upconversion phosphors, UCP. And if the light passes through that, and if infrared passes through that, then without, I mean, of course, there is energy conservation and all that, but a part of the energy gets, a good part of the energy gets converted into PAR. So this is Kavya's work, her MS work, and this, she essentially showed a proof of concept where she coated the covering, she coated the surfaces of the vessel with UCP, an appropriate vessel, and then light passed through that. So without UCP, she had standard biomass. With UCP1, she had 2.8 times, and with UCP2, she had 1.3 times. UCPs, of course, could be very different molecules. So two different types of UCPs. She used a laser of 654, which was the infrared region. And this was published in Biotechnology journal. It's a reasonable journal. Good idea at the time. So this is the overall thing. You have market value versus market size. The biomass diesel is actually market size is huge, but market value is quite low, and that is the challenge there. Whereas as you go up, the algal species produces a lot of products. As you go up, especially to pharmaceuticals, some cosmetics, then you can get very high value products. So any of these can be improved with these strategies. All reactive species based. And where is that? Okay, let me play you a video and we'll finish with that video, which shows it was a video made for an abstract of the paper that was published in Biotechnology Bioengineering on the use of reactive species to improve bio-oil productivities. Okay. That gives you an overall idea of where we are going. So I'll play that 4 to 5 minute video. This was liked by people, so it stayed on their website for quite a few weeks, which was quite rare at that time, 2013. Let me, I thought I had it. Okay. I have all these slides which are covered in the video here. Let me play you the video. Welcome to this abstract. You're able to hear? We all know that bio-oil from microalgae is an area of current research interest. The process of making bio-oil from microalgae is quite simple to describe. Nevertheless, there are no commercial plants across the world that utilize this process to produce bio-oil from microalgae. That is essentially because there are very many challenges to this particular process. If we focus on the upstream side, we can consider getting sufficient cell concentrations as well as getting each cell to have a sufficient amount of bio-oil in it as two major challenges. In this particular work, Kavya Menon, that's Kavya, that's Ranjani, and I have looked at some. The other one was Archana. Now let us look at stress. People have considered various kinds of stresses to improve the yield of bio-oil or the productivity of bio-oil from microalgae. When we think of stress, the first thing that comes to mind is its relationship to the reactive species. In this work, we focus on the reactive oxygen species, and especially the hydroxyl species and the superoxide species. In fact, we propose to use the specific level of these reactive species or the amount per cell as quantitative marker of stress, irrespective of the means that are used to create this stress. And one of the first questions that comes to mind is the reactive species react very fast. That's Steffi. So the reactions are so fast, how can they be considered as markers for something? Nevertheless, we have found that these have provided us very useful quantitative information in our studies as earlier. And this difficulty can be resolved by considering the pseudo steady state aspects. Since these reactions are so fast, you can consider them to be at pseudo steady state levels in comparison with the kinetics of slower processes such as metabolic processes or slower processes. In this work, we have considered two conditions that are perceived to cause stress. One is different nutrient level and also different frequencies or wavelengths of light causing stress. The model system in this particular study is Chlorella vulgaris. Cell concentration versus specific hydroxyl and specific superoxide. These will be the. This was a required reading for you. Something interesting happens in the case of neutral lipid levels too. Let's just look at neutral lipid levels versus specific hydroxyl levels. When all the data are put on the same graph, there is a relationship that we see. And there are other interesting results in the management. The findings That's Archana. Provide a step for us to rationally design the stress-based strategies for improving bio-oil yield from microalgae possibly. And personally, there are more interesting results, such as questioning what exactly stress is, the very notion of stress. Kavya, Ranjani, and I warmly invite you to read the paper. In fact, we have made special efforts to make the paper easily readable. The title is Stress-Induced Lipid Production in Chlorella vulgaris, Relationship with Specific Intracellular Reactor Species Levels. And Biotechnology, the funding that was provided by the Department of Biotechnology, Government of India, the Department of Science and Technology, Government of India, and the Divishri Fellowship by K Suraishkumar, a distinguished alumnus of IIT. Happy reading. Yeah. I'll give him the entire video. It was made here, so made by our NPTEL set. ICSR, there's a studio, right? Yeah, they made it. They make these videos. So that's the backstory for the papers that you read. So it gives you a different perspective and so on, or the doer's perspective. Right? Next Monday is a holiday. Next Friday is also a holiday. So we have only one class next week. That doesn't matter. We're doing fine in terms of coverage. So next Thursday, I've opened up the nanobiosystems. I think 3 papers. Please read them. They're all Archana's work. Her ideas, her work, and she did well. She did very well. So we'll start out with an incentive as usual, and then talk about it. Right? Any quick questions, comments? I took a class. That's why I wanted to have the extra class. Okay, it's always good to go back and do nostalgia part. Only the nice things are recalled, not the horrors. But anyway, no, I things worked out fine. There's no major issue. Okay, then see you next Thursday at 10. See you.